All right. In the slide deck, there is a 2 or 3 page how to do this. And it's grossly oversimplified, but if you go through those steps, it will get you started, and it's based on what we did here today. 2 things to know: it's a quick start, seat of the pants, get you up and running. If you put that in front of a former controls guy, he's going to look at it and say, but wait a minute, there's all kinds of stuff missing in here. Yes, there is. This is specifically targeted to get you guys up to speed doing closed loops in FIRST Robotics with the parts that we have. If you go study this in college, it will take more than a day. Also, it is not a comprehensive tuning solution. It'll get you close. You can get it better if you spend the time and understand and play around a little bit. A lot of this is experience. I encourage you to play around. Put a robot up on a stand where you can't hurt anything and mess around with it. All right. The quick guide to velocity tuning. Make sure everything is zeroed. Make sure your encoder is in phase with your motor. Run everything and make sure it works. If your physical plant is broke, it will not work when you close the loop. Start with select velocity mode. Increase F until basically you run close but not quite the right speed. Increase P until the loop goes unstable. Cut P in half. Then mess around dynamically with F and P and say, okay, what is my error in the range I'm running? If you remember, when we were messing around with velocity, we got it to where it was like off 10 at the high speeds and off 15 at the low speeds. Look at what that error is. Make I 1.5 times, or I zone 1.5 times bigger than that. I zone's got to be bigger than the biggest error you could have residing after P and F. Otherwise, I won't kick on. And you can watch. It's very easy if you're watching all these values to see, okay, I got that too tight. I have a big enough error. I's not turning on. That's why my loop isn't zeroing. Increase I until things go unstable, then reduce it slightly. You don't have to cut that one in half. Once again, I is likely 1/100th of P, and D is about 10 to maybe 100x, depending what's going on. Once you get that done, you go back and start messing with the numbers and look at the effect. Once you have it grossly set up, go back and mess with P. You might be able to make it better. You saw us dial some D in, all of a sudden I could go back to P and do some more. These things interact. And yes, there are 1 million answers, and most of them are wrong. Get some experience. And you may find that limiting your max forward and your max reverse will help stabilize a loop if you just don't need the speed to get there. A position loop, similar story. Ensure everything is zero. Once again, this is wrong. It says F in there. That should not be in there. I have to fix that. So I have to do a cut and paste from the first one and then chop it up. I missed something. So line 4, forget about that. 5, increase P until things are happy. Actually, I said if it's a static limiting axis that always looks at the...
Yeah, I think that's right.
Oh, actually, I did do it correctly. Bonus.
It has to be a static load like
If there's no static load, leave F at 0. All right, do P, then do D. You might be able to get to your answer. If you're not, because down at 9 it says, if you need more precision, all right, then go dial in I and get your precision in there. But if you can do your position loop with PD, it'll be a lot stabler and a lot easier. So there you go. That's your cheat sheet of how you do this stuff. So the trivia question. You can tune a piano, but you can't tune a fish. Where on earth did that come from?
REO Speedway.
When were you born?
85.
Okay. He wins. REO Speedwagon, 1978, an album. You can tune a piano, but you can't tune a fish. That's a test of everybody's age. All right. So, it is 4:44. I'm here as long as you guys want to chat. If you want to blow out of here, you can do that. We've got our competition robot from this year here. I've got all the data that I will show you on anything. Mark's here to answer questions. Corey's here to answer questions. It's up to you guys what you want to do with the rest of the time. So, any classroom questions you have? Yes?
Is there any way to graph this information during matches so you can analyze it afterwards?
Almost like we paid him to do that. Yes. It was tricky before. With this system, Jeff's got this all set up where you can run this with your competition code. If the grapher isn't asking for anything, the overhead on the Robo-Rio is virtually zero, right? I think it's virtually zero. So you can build this into your competition code, and while the drive team is driving, you can fire up a laptop and start watching this, which is really, really helpful.
You can't do it in competition, but you can do it with
Yeah,
competition code.
First would frown on it, and actually they may have the ports and crap locked. But no, on practicing, yeah, you can absolutely do that, and we do that all the time. Now, no, the more stuff you're watching, the more work the Robo-Rio is doing to get that information pushed up here, out through the Ethernet to get to the grapher. So you could change how the Robo-Rio works if you are watching too much stuff. So keep that in mind. But yes, this is designed to run side by side with your comp code, and the only burden on the Robo-Rio is how much stuff you're asking. If you turn the grapher off, literally there's no load on the Robo-Rio. Today we have this written in Java. I think a lot of people are using Java. Jeff, if there is a C++ team, how many of you guys are doing Java? Okay, who's doing C++? And who's doing LabVIEW? Okay? I don't think we have any hope of an answer of you running this live on a robot in LabVIEW. Does this have any hope of running on a Robo-Rio that's running LabVIEw?
So you can do all the tuning.
Yeah, you can do all this.
You can tune all your axes with the utility. The grapher, so if you integrated this with your robot, there's a pretty, and it's documented up on the website, there's a pretty simple JSON format data exchange between the robot and the grapher. You could probably recreate that pretty easily.
You'd have some work to do it with LabVIEW if you wanted to watch your live robot, but certainly testing, you just load the Java Virtual Engine up on the Robo-Rio and you fire up TCT and you put your grapher up and away you go. So pretty easy for anybody to do this testing. And if you actually have the thing coded in Java, you can stick that on your compbot, and when you run around on your practice room, you can test that.
What about the C++ people?
C++ is actually probably easier. Jeff, if folks have C++, same story, you just put a Java engine on there, and you certainly do it on the bench, but when you're out running the code, probably the same problem with the as with LabVIEW.
Yeah, you'd have to port it.
Yeah, you have to port it. So if your comp code is not Java, you won't be able to use this while you're actually driving your real robot. You could certainly put a Java engine on it and manipulate and tune all this stuff up on the bench, then switch over to your competition code. For those that have stayed away from Java because they're worried about the garbage collector and the time issues, which is why we stayed away from it until this year, and Jeff finally proved we could manage it. And we really went there because the cheesy poofs had gone there, and they're pretty clever boys, and they wouldn't have gone there if it wasn't manageable. There's ways to deal with that. And when we look at Java, that is a language that kids are by far most likely to use post-first. And it's the biggest way to serve the kids. So that's why we've gone there. And at this point, FTC, Java's all they got. So I think you're going to see first migrate towards Java for lots of different reasons. Yes?
How long did it take to tune the PIDs from this robot?
And there was a question earlier asked about that. For example, when we put the shooter together for the first time, it did not have anywhere near as much flywheel on it. Basically, the inertia on that shooter was nowhere near as big. And we fired it up, and I put P as high as I could get it. Probably took me an hour to get that optimized. And we stuffed some balls into it, and it was way too slow recovering because P wasn't high enough. If I made P any higher, it oscillated. Also, when you put the ball through it, there was no inertia. It sucked a lot of energy out of it. That thing slowed down. So we machined up a flywheel and put that on it, and much as you saw here, huge difference. That was good, let's do more. So we put a second flywheel on it, And that thing's got as much flywheel as we could fit in it. And so retuning it each time was actually a pretty quick process. No different than doing this. It's changing the physical plant and knowing I need to do that to get someplace. And the whole goal was you had to recover that thing in 100 milliseconds before the next ball gets there. And that gets to be tricky. But probably an hour or two to tune that the very first time. On any of the given axes, it's probably an hour or two to tune them. As long as you don't get caught by, as I always taught my daughter, silly, stupid mistakes. Things that after the fact you look back on and you knew better, you just weren't paying attention. Make sure when you start, it's all zero. Have a spreadsheet or a notepad or something at any given moment, know what you have programmed into the thing. It is unbelievably easy to lose track of where the values are at, and suddenly you think they're one thing, they're another thing, you're working in a different area, and you will light hours on fire. If you keep track of it, you will actually find you can tune most of these axes pretty good in an hour or two.
And to be fair, Jerry said there's 1 million wrong answers and 1 right answer. There's actually 500,000 wrong answers, 500,000 partial credit.
Partial right answers.
Partial credit that would probably work, and then 1 right answer.
There's 1 perfect answer. There's actually 100 okay, good enough answers.
Yeah. And to that point, you might be able to tune it faster because you're willing to run an over-dampened thing, which would work just fine, right? Jerry tends to try to get that last little overshoot bump going. It takes him a little bit of time.
Other questions? Yep.
How do you implement all of this stuff into actual robot code?
Jeff can probably answer that question on TCT, which is what you would need to implement the RoboRio. The grapher just installs on a laptop. So that's just and we do the complete package. You put that in a zip file and it does everything. But I'll let Jeff answer the question on how you would get TCT integrated into your comp code.
So we, when we send out the email, it'll point to a website that'll probably outline that. There is a standalone library that has all the robot resident telemetry code, the stuff that reads the talons and sends it to the grapher. And it's got a pretty simple interface to
So it'll be follow the directions.
And you guys are guinea pigs. If we turn you loose and you have trouble, it means we haven't got our work done yet. We'll figure out how to get the recipe right so it's executable. Other questions or other thoughts or comments? Anybody want to know anything about that monster? Yeah.
Okay, do you use 775s for everything on there? Do you use 777s?
On that robot, it is either a 775 if we needed the horsepower. So on the drives, on the climber, on the intake that sucks up the balls, that's all 775s. The azimuths are all 550s, and some of the gear handling underneath of that, the gear handling is not a high energy thing. Big gear ratios, it's not moving that fast, that's 550s as well. But I think the only bag motor on that is back on the elevator for the shooter. And honestly, Mark, can you remember why that's a bag motor versus a 550?
RPM.
Okay, we were trying to slow that down, and that is the slowest small motor.
Otherwise, you couldn't get you'd have another stage of Vex or something on it if you ran a 9015 or something.
So we've become believers in 775s as the drive motors, but there is no margin. If you have a younger team and you've got plenty of other things you're trying to solve first, you might not want to do that because you can beat a sim to death. You can have a 775 destroyed in the blink of an eye if you step over the line. We've decided to go there because it saves weight and there's performance and everything. There's not a lot of margin. And honestly, on the 775s, we run those a specific length of time and they are changed out. It is a disposable item on that robot. And we can change all 4 drive motors in probably 20 minutes, and it's going to be way faster on next year's robot.
What, how many hours do you put on a line one before you swap it out?
If it has not gotten hurt, we might run those drive motors for 30 matches.
Well, the ones that just came off of it were FOC and WMRI, right? You had
The
one
ones that
that
just came off of it were FOC and WMRI,
and
and
you examined them.
they were not perfect. If we were gonna compete with that more, they needed to be changed.
How many hours on the practice field will you run a set?
That was very impressive. Our practice robot motors lasted a really long time until they practiced defense.
Yeah. Then they lasted not very long.
Okay.
Because I don't think there was any current limit on the when they did the defense. There was no. I don't think
We
there was
learned a
current
couple
limit.
of things on the 775s. You probably don't want to punch more than 50 amps through them ever.
And we have our experience is the copper is not a problem. It's a brush. So
The brush assembly is your weak link.
you know the copper actually is pretty happy, especially with a little bit of airflow.
At 30 amps, if 30 amps was your max,
And you're spinning.
you could, and you're spinning, you could run those 775s forever. If you are stalling them, or if you're running them in the 50 amp range, there is a stopwatch running during both of those events, and it ain't a big stopwatch.
You said the limit they put on those was 5.0 or 1.5?
5.0. 5.0. Yep.
During the road season, 2017.
Yep.
How did Stryke Force bring together different projects, design ideas, into one championship?
Panic is always good. Because Mark, how much time do we have left?
We have no time.
We have no time, we're out of time. The reveal goes up, the video's over, and the next word out of his mouth, we are out of time. But wait a minute, we got to say you're out of time. Our process. There is the reveal video, and we'll have everybody in the room, mentors, kids, everybody who watched the reveal. We will spend the rest of that Saturday picking apart the game. Everybody's reading the rule book. We're understanding what are the constraints, how do you score? What's the scoring in auto? What's the scoring in tele? What are all the different scenarios? And at the end of the day, our goal is to have decided this is our strategy for scoring points. And depending on what the game is, maybe you try to do everything. This year we tried to do everything. What is your strategy going to be? We do not design the robot in the first day. You design the gameplay. How are you going to play the game? You presume magic's going to happen and the robot will actually do it.
If you talk about the robot, you're shushed.
Yes.
Can't talk about that on the Saturday.
And with a bunch of engineers in the room, we are shushing ourselves constantly because you just keep falling right into, hey, we can do it, so let's shut up. So that Saturday is about really thinking through the gameplay, and it's about what's the robot going to do at the first district event, and what's it going to have to be capable of at Worlds. You're probably not going to have your Worlds robot completely ready to go at the first district event. You have to choose what pieces you bring online and architect in the ability to continue to work and make it better and better. We did not have, when you look at what you would call the full weaponry all maxed out, that actually didn't happen until IRI this summer. It was not actually wide open at St. Louis. It shoots a heck of a lot faster now than it did in St. Louis because there was still some stuff we were figuring out. But we architect the gameplay and think about how we're going to stage that out. And we always want to build enough robot to compete at the world's level. We may or may not get there in any given year. We then come back on that Sunday, usually starting at 1 o'clock or so, and the kids are in the room, the engineers are in the room, and we go at the robot. We know what it needs to do, so the game specification is now done. We have to design a robot that's going to do that job. And that gets a little bit easier each year as you build more and more experience of the reality of what goes on in the next 6 weeks. and we will architect the robot. So by the end of Sunday, that architecture existed. We're going to do a swerve drive. We're going to suck the gears up off the floor. We're going to bring the balls in like this. This is the rate you have to suck balls in. It's going to go in a hopper. The hopper's going to have to puke the balls into the shooter at this rate. The shooter will have the ability to go up and down and change its range and do all of that. We're going to handle the gears this way. Mechanism-wise, are all the details worked out? Maybe not.
No.
But grossly, you know, this is the volume for the robot allotted for that. This is what we're going to do. We will then go on Monday, and it is how fast can you rapid prototype with duct tape and baling wire and wood and drywall screws. It doesn't have to be pretty. Prove your concepts work. If they don't work, throw it in the trash now and build another one in the next 30 minutes. Get to workable proof of concepts as fast as possible. Interesting story on figuring out how to throw those freaking wiffle balls. I almost need therapy along with a number of the kids. We shot a lot of wiffle balls. And it would not be uncommon probably in an evening.
Shooting 20 at a time.
Yeah, so we would shoot thousands of balls in an evening. I mean, I don't know how many balls has been through that thing, but it's a bunch. So you get your proof of concept done, and then you say, okay, we now think we know how to do the real finalized design. It's all completely CADed. You can't do anything that complex without. That whole thing is CADed, and then we start what we would call prototype fabrication. And we will start building what we think the real robot is. We build a competition robot, and we build a practice robot. The practice robot is the first robot we're building. When we start, we think it's just like the competition robot, and you start assembling it. And guess what? You learn some things along the way. You can maybe cut it, chop it, whatever, fix it. You get it to where you're happy. And the competition robot tends to get assembled at a 2-week lag to the practice robot. That's usually about how long it takes. All right, we're actually comfortable, this part is sorted out. Execute that on the competition robot. Which means you better have your practice robot pretty much done at week 4, because in week 6, that competition thing goes in the bag. And that's really the cadence we run, yes?
There's 2 parts to the practice robot. The practice robot only had ball intake and a hopper. There was only 1 shooter made, and there was only 1 gear intake made. That's swapped between the 2 robots within the weight of box.
So you've got 30 pounds you can have for spare parts, and on certain mission critical things that are going to be highly, highly tuned, we might only make 1 copy and design a predictable interface to where you unbolt it off the practice bot and you bolt it onto the competition bot, and that's what we use our 30 pounds for.
So we got lucky this year. The shooter and the gear pickup was less than 30 pounds.
And we purposely work and say, okay, this is a complicated part of the robot. That is, those elements, they need to fit inside of 30 pounds. So if we only want to build 1, or worse yet, you need to have it out of the bag to work on it, then you've got a way to do that. So we leverage those 30 pounds to maybe only make 1, or to actually access that part of the robot and keep going. The nuances in that shooter to get to the point where you could shoot balls in the hopper from any place within 20 feet of the goal, there was a whole lot of learning went into that. That was not obvious. Other questions? Yes?
While looking at your robot, I noticed that you have an NavX MXP on there. What functions program did you use?
Okay. We are using, really, the gyroscope azimuth. So we use that for the drive system. And that's a full swerve drive. And what goes on is the code is looking at the NavX to figure out what direction the robot is pointing. And when Jack shoves the stick forward, it is field-oriented direction. When he shoves the stick forward, that thing is going down the field. If he yanks the azimuth and spins the robot sideways, the NavX says, hey, you just spun sideways. I'm changing what direction forward is. Forward is still that way. So I'm still going forward. And the inertial system does that. He then switches it back, and now he's driving the robot forward. Oh, you just went 90 degrees. I'm moving forward 90 degrees back forward. At the end of the day, what this comes down to is the joystick for Jack, when he tells that robot to go down the field, the center of that robot is going down the field. It does not matter what he does with the azimuth. This is down the field if he doesn't touch the azimuth. And if he yanks it and he's spinning the thing as hard as he can and sends it down the field, now it does this. But the center of the robot is going down the field. So we use that NavX as an inertial guidance system to manage the azimuth orientation of the robot, and that way the driver doesn't have to figure out, okay, now I'm coming at me, this stick is backwards. That stick makes the robot go the direction you push it no matter what. This other stick controls rotation. When you watch some of the maneuvering he does, that's how it happens. If you didn't do that, maybe a gamer who spent hours and hours and hours could get that right, but this makes that very achievable. So that's the primary thing we do with that. It's got magnetometers, tilt sensors. It's an amazing thing. You can do a lot with it. That's all we do with it now.
Literally just using it as a
As a compass.
I say a compass, it's not using magnetics, but, so, 1 out of the 9 things.
And folks will ask about the drift rate. Any inertial guidance system has a drift rate on it. That thing drifts about 1/2 degree in 2 minutes. So the uncertainty of what's down the field drifts 1/2 degree during a match. It's perfectly fine.
And yeah, the humans PID takes care of that.
Yeah.
I wonder, because I was driving Robotics, and you would look like you were like facing that way, but then you came back at me, and I'm like, what just happened?
Yeah, he just, and it sounded like, oh, Jack, he just pulled the stick that way.
Yeah.
And that's an example of saying, okay, we can do a job in hardware that offloads the human that's actually a good job to do in hardware. Some jobs are not good to do. Let the human do it because they're really good at it. Other questions? Any questions about the robot and how that thing works?
I guess, again, one more
Yep.
with your interface.
Yep.
Sentinel interfaces. So you pretty much use those for any type of encoders. What else do you use?
Anything we're feeding into a Talon. Encoders, both digital and analog, limit switches, if we're feeding any pulse stuff into it, any voltages into it, anything going into the Talon goes through a Sentinel. And it is set up to do all of that. It's got some programming pins on it. You can scale whether you want your sensors to be 3.5 volts or 5 volts. It protects the Talon. Any interface to the Talon, that's what it does. And it has indicator lights on it where you can see your quadrature banging. You can see your limit switches hitting. And it's got a 5 volt and a 3.5 volt come out of the Talon, so if you somehow collapse a rail, you know that too.
Afterwards, you can go and eyeball them and
Yep.
play with them up there, and his Saab's got it.
Yep, you can see
Got
what
it
all
on.
they do. We got them on here.
One thing that I thought was quite novel this year is, I don't know, you always have some sensor that you run back to the RoboRio's DIO, right? And on that robot, there is a sensor to see the gear coming in, right, to stop driving a motor. Normally, you'd run that sensor back to the RoboRio into a DIO. There's no reason, and we did it. We ran that sensor into a forward switch on one of the Talons that's down there amongst the guts. Told the Talon to ignore the switch, but report it up. So now you don't run a wire all the way up to a DIO. You simply run it to any Talon that's not using a forward reverse switch, and you can read this switch.
And just reads it back through the cable.
Yep.
So the way to think of it, there's actually quite a bit of DIO going into the Talon, and you can tell the Talon, I want to use that as my feedback. But that doesn't mean you can't be feeding other things into it and have the Talon tell the RoboRio what's going on. Now, you can't feed in 2 quadrature encoders because there's only one set of hardware. But if I'm actually using an analog pot for my encoder, I could feed a quadrature encoder into it. The RoboRio could ask all day long what's going on, and the Talon will tell it. You just got to pick which one you're going to use in your feedback inside the Talon.
Does the Talon be used to run a digital servo?
Actually, like the hobby servo?
Yes.
No.
Yeah, Canifire will.
Oh, Canifire will?
Yeah.
Yeah, you plug it in a RoboRio, or I think the Canifire, they have a servo drive right on it. So the Canifire is a little Wizmo from across the road that goes right on the CAN bus, and it'll drive a servo. Drive LEDs and does a lot of interesting things.
But digital servo, that's the difference in the question. We use analog servos quite a bit. But when once you use a digital servo,
RC servos.
it goes somewhere.
That I don't know. I don't know if they've got a mode to drive a digital
Yeah, and-
servo.
And I think, I don't know, I
And
tried
I
to.
don't believe the RoboRio will drive a digital servo.
Okay,
Okay.
yeah, because that's a true digital servo you're talking about.
Yeah, it's rails and a bus versus the
Most
pulse
of
width getting-
PWM. Now, what I just recently ran into this in a non-Strike Force thing. Some servo people will call their servo a digital servo when in reality it takes a regular PWM in and it just digitizes it inside, and that just caused confusion. So I don't, when I pick up one that says, oh, it's a digital servo, it's like, okay, is it the digital one you talk to, or is it just digitized, you know? So I think you're stuck with analog servos.
Other questions, comments? Yes? Okay. And we've become big believers in vision. We used it for the first year on Stronghold last year, and obviously this year pretty extensively. What you have going on there, and this was overkill because we did not want to run out of horsepower because we weren't quite for sure what we're doing. There is a point gray camera on that, available for about $350. That is a high definition USB 3 camera, industrial grade. You can tell it to do a lot of different stuff. That is rigidly mounted to the shooter. You don't want that to move. That then feeds into a Jetson TX1. And a Jetson TX1 has a teraflop of processing capacity. It is a really big horse. And NVIDIA's whole goal is they want to get everybody fired up to use the GPUs that they manufacture. And that thing has got 192 CUDA cores on it over in the video processing area. That thing is a horse. As it turns out, this year, we never figured out how to pipeline the images into the CUDA cores. Plenty of power. Once you're in there, poof, you can instantly be done. We couldn't get the images in that memory and back out quick enough for what we were doing. There's two little ARM core processors on it. We ended up doing all the work in that. And all the math happens there, where basically then the RoboRio is told, this is how far off a center you are. This is the elevation in a number. All the processing, all the rest of that, the lights, all the binary imaging work, all that happened in the Jetson. And then the Jetson simply fed, much like a servo, okay, when you're trying to line up, this is how many pixels you are from zero. And there's a position loop in the RoboRio using the Jetson as its encoder. How far away from zero am I? Driving the robot to azimuth. And the Talons are running in a velocity mode on the wheels. So we turn all the wheels at 45. It's all set up in velocity mode. And now the RoboRio is in charge, telling the robot, all right, run your wheels at this speed. Okay, the robot's turning this way. And the RoboRio is watching the incoming data from the Jetson. And it's a position loop. And as you get closer to your answer, you slow the robot down, and it's the same tuning game. If I put too much P in it, my robot goes past center and does this. If I don't put enough P in it, it goes, just like you learned here. So the camera and the Jetson was telling me where I'm at. RoboRio is the position loop. Talons are all programmed as the velocity loop, so this is like motion magic on steroids. And that's what's going on. It's complicated, but it's not as complicated as you think. The key thing is get each block done, make sure each block does what you need it to do, and then integrate it. And somebody's got to understand how it works, because when it's broke, crazy stuff happens.
Now, there's a whole process of stripping the colors out too that Jeff would.
Yep. We actually found some pretty nice little green LEDs that are brighter than the sun, and they're pretty small, and we can light the reflective tape up pretty good, and Jeff has helped an awful lot with figuring out how we get all that stripped back out and pick the colors and do all your bounding and make sure you only see the stripes you want to see. For those that watch us at State, we had a really good time on Ford Field, and then the thing wouldn't shoot for crap in the championship. And that was a case where, and we actually to this day don't know, there were some artifacts reflecting green light, and we were vulnerable to things looking green that was more than the reflective tape. And the Jetson could not come up with an answer where it said, I can see those. I see a bunch of stuff, I don't know what's what. Robo Rio, I got no information for you, and it wouldn't shoot. And so you've got the drive team out there, and literally when we went to the finals, because this worked flawlessly every day at States until you got to the final elimination day. And it was like somebody did something to the lighting or whatever in there, and we went in there, and it's like, what the heck is wrong with the shooter? Won't shoot. And we thrashed like crazy on 1,000 different things, and I kid you not. Corey is going to the final rounds, and man, if I don't have a shooter, we're losing. I'll let you know if you have a shooter when you try to use it. Because we don't know. We don't know what's wrong. And I think I had actually worked in finals on Ford Field, I think.
Twice.
I don't think it worked at all. And
It would either work or it wouldn't work, and now they're thinking we did it.
Yep. And so then, and over then on whatever field it was where the final round was, we pretty much didn't have a shooter. And so that, some interesting lessons. We did a lot more work on making that more robust. And for the most part, I don't think we had a problem after that. Do you remember, did we ever, I don't think we ever had any problems after States with all the stuff we did. No. Any other questions? Did you guys find this useful? Do you think you walked away with something versus just being unconscious for all day? Cool. The slide deck will be available. We will actually, we'll do it PDF. We'll also send out the PowerPoint. If you have the PowerPoint, the animations will actually run. If it's a PDF, the animations will just be a picture. And look for an email where you've got instructions of how to upload this stuff and try it. We fully expect there's going to be problems, and that's why we want to do this, and we'll get the problems sorted out.